So for this, we want to look at the motion of charged particles in magnetic fields. We have this here is a charged particle, and it's moving to the right. That's sort of what that green arrow is representing, that is the current velocity of this charged particle. So it's moving directly to the right across the page. We have a magnetic field, which, as you've said, is into the page, right? That's the axis, like you're looking at the back of the arrow. So the question is, in what direction is the force on this particle? The result? Up. All right, so let me check. So if I point my thumb of my right hand in that direction, and the palm, my thumb has to point in this direction of my right hand, and the palm of my hand has to point into the page, right? So it's sort of like, that means we have to be looking at the bottom of my right hand here, right? And my thumb out that way, so my fingers have to be into the page. My palm would face that direction, right? The palm of my right hand would face up. So that means there is a force in the up direction, right, which we can indicate here. Okay, we got a force. Okay, there's our lovely force in the up direction, right? And note, again, all three are perpendicular, right? The velocity is to the right, the magnetic field is down into the page. So if you look at any, like, all three of these are 90 degrees to each other, right? Okay, so what does that mean for the velocity? If it has a force in this direction, right, up, and it's currently moving to the right, it has no force to the right. So what does the velocity of this thing look like a moment later? Whereabouts would this particle be in some later time, right? If it's got currently has this velocity and it has that force on it, would you expect it to be at A, B, or C? Yeah, I would say B-ish, right? About there, give or take. So let's just go with B, right? Certainly, it has this horizontal component or to the velocity, so it's not going to lose that. So maybe it ends up at B. And the velocity when it gets to B should be about like that, maybe. Right? It's still got the same x component of this, right? Nothing's affected that. But it's had a force, right? So it's been accelerated in the up direction. So it might look something like this. So now the question becomes, okay, in what direction is the force on this thing now? Right? Say, okay, well, I got to use my right hand again. I got to point my thumb in the direction of the velocity. I still have to point my fingers of my right hand down into the page. So basically, I just hold my hand would look like this, and my fingers would be going down. Right? You wouldn't see it. You wouldn't see my fingers from this perspective. So that means the force is once again perpendicular. Right? So the force would have to be in this direction. Yeah, we'll go with that. And so it accelerates in that direction, right? It preserves this component of its velocity, but it accelerates in that direction. So that means some little bit later time, it's here. And now it's got a velocity more like that, let's say. And you can repeat this process, right? Use your right hand, point your thumb in that direction, keep your palm facing, or keep your fingers of your right hand pointed down into the page. Now your palm faces over here. Okay. And so what you should end up seeing, and you can, again, try this with your own hand, right? You should see this. Oh, sorry, that's not a good drawing. And the force will always be perpendicular. Sorry. Right. And again, you can check that with your hand, right? If you do this with your right hand and you sort of hold it so your fingers are pointing down, you'll notice as you keep turning it, right, your palm is always facing a different direction, effectively some like center of curvature, if you will, right? And so you end up with a circle, right? You end up with this big you end up with this sort of circular path, although that's a horribly drawn circle, but in reality it wouldn't be so horrible, I don't think. Okay, let's look at another example. We have, now just look at, forget the text here. What should happen here? We've got the velocity of a charged particle moving to the right. We've got the magnetic field indicated, which also right now looks like it's going to the right. In what direction do we expect there to be a force on the particle? If we look at this, now remember, the key to the right-hand rule is everything has to be perpendicular, right? 90 degrees. So you point your thumb in the direction of motion, right, which is here. And then you have to point your fingers in the direction of the magnetic field, which is the same direction. So no force, right? If they're not 90 degrees, no force. And you can go back and look at this, right? You can say, well, remember, what made something move was effectively like interacting magnetic fields, was the way we sort of looked at it. We said, look, if you have a magnetic field here, right, and let's suppose this is a magnetic field actually shown, it's as if at any point you've got like a bar magnet, that's the north, because it always points to magnetic north, that's the south. And this moving particle generates a magnetic field, right, perpendicular, sort of in a plane of motion, if you will, right, perpendicular to its motion. So if it had a magnetic field going around it, we'd have to represent that. Remember the right-hand rule, point your thumb again in the direction of the velocity, curl your right hand around it. You would see, okay, my fingers on top are coming toward me, and on the bottom they're going in. So that would sort of represent, if you will, the magnetic fields, right, of this. And you'll note that these two magnetic fields are 90 degrees to each other, right? They wouldn't really interact, right? They're not, they need to be parallel to each other. The magnetic fields, right? When it's like you've got another bar magnet coming out of the page and another one, going to the right on the page, they don't interact. They don't do anything. So in this case, as I presented it to you, you got a big nothing. But I put some text here because I knew I couldn't draw this very well. So the text here says the charged particle has a component of its velocity that's coming out of the page. So this makes it different. We want to now determine the motion of the magnetic field. So that means if we consider the velocity here, right, we have to imagine part of this velocity actually coming out of the page. So it's like, right, we sort of got it that. So now try again. Point your right thumb coming out of the page and your right fingers in the direction of the magnetic field. For me, that means my palm is facing up, right? So there would be an upward force here, but it would not lose that component, right? So you could also say this component of the velocity remains unchanged. I'll write it that way. This rightward component of the velocity remains unchanged, but there is enough, and you'll have that same effect, right? If you imagined a velocity that was only coming out of the page, right? Well, the initial force would be up, and you'd be able to basically turn your hand all the way around, right? You'd be able to sort of go in a circle like that. And so as a result, what we would end up with here, the velocity we sort of end up with here, and I'm sorry if I can't draw this really well, but we would end up seeing sort of a corkscrew, if you will. And this would be the motion. Since, as I said, this sideways component is unchanged, but it just goes in a circle, like into the page and out of it. All right, so what we want to do is if we do have, well, this would be a weird circle to have to find, but even just something like this one up here, we want to figure out, well, what is the radius of this circle, right? How do we find that? I kind of wrote out the derivation for you. To find the radius of the particle's motion, we just use the fact that F equals ma. The magnetic force we've seen before, that's just QVB. That goes back to the equation we used yesterday. Now, I will note I'm only considering this equation here is only considering the perpendicular component. Considers only perpendicular component. Because remember, the actual equation yesterday was QVB sine theta, because we only wanted that. So here I'm assuming it's all perpendicular, or if it's something like this example here, I'll figure out what the perpendicular component of the velocity is and use that. So QVB, that's the magnetic force. Because it's going in a circle, it's centripetal acceleration, so mv squared over r. Multiply both sides by r to get that over to the other side. Right, and then divide both sides by QVB, sorry. So they all cancel, and one of the squareds cancels out there. So it leaves you with this lovely equation right here, which you could use and write down, and just if you had a problem like this, figure it out just like that. So in this example, we have a particle physicist accelerates a proton from rest into a magnetic field that's 4 Tesla, perpendicular to the field. After entering the magnetic field, the proton hits the wall adjacent to where it entered. This means beside, right? 15 meters, well, we don't really know where exactly, up or down or over. We're not given a lot of details of this or a diagram. I made one, but I'll get to that. So we want to know what the potential difference is that the particle is accelerated through. And we know that it's a proton. Okay. So I tried to sort of draw what this looks like, and this is a really key part to solving something like this, is sort of figuring it out and noting some of this information. I'm just drawing. It's not necessarily that way, right? So this part is with the parallel plates. I'm just saying, look, if you have parallel plates, you'd want to orient them that way, right? So that a positive charge would go in to the right as I've drawn it. And that, of course, would generate, we'll consider this to be a relatively constant E field, right? And all you would do is basically leave a little opening. You can sort of imagine that in 3D, right? I've got a hole essentially on the plate, right, where I expect the particle to go through. And right on the other side of that hole is a detector wall, right? So the detector wall, which you can tell that's what it is because I wrote it down. So that's shown here, right? And so we know the particle is going to go into this magnetic field. Now I've drawn the field coming out of the page, right? I've drawn it up. We're told it has to be perpendicular. I could have drawn it up or down, I suppose, but that would have made solving this a little tougher. So I just said perpendicular, and since the velocity of the particle is to the right, out of the page is definitely 90 degrees to something that's going to the right. So as I've drawn it, right, what sort of motion do we expect? Right. Then I give you effectively 3 options here, right? We could have, it could go down like this, right? Once it gets into the fields, that could be the motion of the particle. It could go up like that. Or it could go, it could go all the way straight through. Maybe it's not affected. It could curve out of the page, which I guess that's the best I could do for that as well, or down into the page. All right, I will attempt. Again, 3D is hard, and I'm drawing because, you can't see me here do it, which might actually be a little bit easier. But anyway, let's get rid of that. I don't want that. So I'm going to point my thumb of my right hand in the direction of motion. That thumb has to go this way. Okay. Now, the magnetic field is coming out of the page, right? So that means, right, if you're looking at my right hand, right, you're looking at the top of my fingers here, right? The tops of my right hand. These are my fingers coming out of the page, and my thumb is pointed that way. So the palm of my right hand would face this way, right? If you put your right hand exactly there, your palm would face down. So yeah, so your palm faces down, my palm faces down. This is fantastic, right? So that's what would, and so if it faces down, it's basically that means, right? It's going to do right as it moves your palm, and you can sort of imagine taking your right hand, right, your thumb, again, there's the fingers, right, as the force is in that direction, right, it's going to keep changing it to move in that direction, right? It's going to be like before. And so we're going to end up with, get rid of that, this right here. So now we know this. And this actually would be important because you may want to answer a question like this where it's like, does it hit below or above, right? You want to be able to figure that out. And we're told this is 15 meters. Right, we know this distance here is 15. Okay, so I might say, look, what can I do? All right, well, I know an equation that I just figured out. R equals mv over qb. That seems like a good equation. R equals mv over qb. Now this seems potentially helpful, but let me see. Like the question asked for the electric field, right? I got some sort of E field here. And what do I know about this? Well, I've got some energy. It's going to accelerate it to a certain velocity, right? And so whatever that energy is in that E field, right? Whatever the energy is there, that's all going to be converted to kinetic energy. And so the electric potential energy here, remember, V is just, or electric potential energy is just Q times V, since V is just the electric potential energy divided through by Q, because we assume a 1 Coulomb charge. And that here has to equal 1/2 m. Now here's where it gets a little tricky. Remember, this is little v for velocity. Over here, this is a big V for voltage or potential difference. Sometimes you can even do something like put some little, something to distinguish it or make it different. I probably won't really bother with that, but just, be very careful with stuff like that. And ultimately what I want here is V. I want the potential difference here. And so that's going to equal mv squared divided by 2q. Well, the mass and the charge of a proton, I know, right? It's v squared is really the thing I want. And so that's, again, just if I'm trying to work backwards when I'm solving something like this and saying, well, what's the quickest way I can get to what I want? What do I need? And then I get to this over here where I do have an equation here where I could find v. Right? I know it's going to go in some sort of a circle with some kind of radius, so I can find v. And so that means I can say, what can I write? I want v, so I can rearrange this and say, okay, v equals RQB divided by m. Okay. Now I could find that number. Now you could actually just go and substitute that in here. Since you've got some of the same things like M, R, and Q, I might kind of just do that. But you could also just get the number, right? You could also just say, you know what, I just kind of want that number, and then I'll go back to the other equation. So why not? So that means V here equals, so what's R in this case? What's the radius of this circle? This often gets people. I'm seeing the correct answer quite a bit right now. Yeah, absolutely right. The radius of this circle, right, R equals 7.5. And that's really key, right? If it hits 15 meters, that means the diameter of my circle is 15 meters. The radius is half that. So that's where I've got to be a little bit careful. And so that means I've got 7.5 times by the charge. Let me put the charge of a proton, well, same as an electron, just positive, 1.602 times by 10 to the negative 19 times by the magnetic field, which I'm told is 4, divided by the mass of a proton, 1.67. See how close those numbers are? It's hard to remember. Times 10 to the negative 27. And that gives me a result of V equals 2.878 times by 10 to the 9 meters per second. Okay, pretty fast, gotta say. Now, one of the things too, if you are doing it this way, note I might have even kept another decimal place. Because I'm taking this number and I'm going to sub it into another one. This isn't my final answer, so I don't want too much rounding here, just sort of as a general practice. And then I can take that, remembering that big V here is what I actually wanted. So big V for voltage is, again, I'm going to use that same number for the mass, which was 1.67 times 10 to the negative 27. Then I can take this number I just found, 2.878, divided by 2 times the charge, 1.602 times by 10 to the negative 19. And that means V is 4.32 times by 10 to the 10 volts. I always love how it's V equals V, but you get that it's the potential difference equals 4.32 times 10 to the 10 volts. And that would be sufficient to make all this happen.